Go back. Okay, we are starting. Okay, sorry. All right. Good morning. Welcome back to Calculus 2, Elements of Calculus 2. We are looking at problem number 5 for the pretest here. So this has we're going to generate a fourth degree Taylor polynomial for this guy right here, 6 over 1 plus x, 3x squared. Okay. So what I'm doing with this, okay, so I can go ahead and grab this guy right here. We look at number 5. Make sure we have good instructions here. Fourth degree Taylor polynomial, also figure out the radius of convergence. So what I want you to do with this problem is I want you to go down to the section where it has the Taylor polynomials listed for us, find the one that looks like it's going to be the best fit. Okay. This thing doesn't have an e in it. It doesn't have a natural log in it. It looks like a fraction. Let's go with the fraction. So it's 1 minus 1 over 1 minus x. Okay, so this is 1 over 1 minus x. We're going to say 1 over 1 minus u is equal to, and we'll go ahead and write this thing down as the u's values rather than this piece right here. So we have 1 plus x squared plus x cubed plus dot, dot, dot. I do not want you to recalculate a Taylor polynomial with this. Okay. Okay. We'll go to view the fourth. Okay, plus dot, dot, dot. Okay. Now, what this is going to look like, I need to recast my problem that was given to me in the form that it looks like over here. So this is really 1 minus negative 3x squared. You see how that's going to be a 1 plus, if I put the minuses in here, it'll look like this. But if I leave the minuses in, it will look like 1 over 1 minus u. Okay, so this is very powerful. If you ever end up watching a video series, YouTube video creator by Black Pen, Red Pen, he uses this all the time. And I have to admit, this is a very nice Taylor series for 1 over 1 minus u. It's very, very powerful to do that. A lot of times we use this to break a lot of difficult to solve integrals. So this is a very, very powerful technique that you're going to have at your hands with you. Even still, like you never dealt with sine x, but sine x and cosine x also have Taylor series. So if you ever have to deal with sine x or cosine x, you could always replace them with their Taylor series. Then they're polynomials, and there's a couple of things that you still don't get because they're repetitive kind of problems. They cycle, but for the most part, you can approximate your sine and your cosine with the Taylor series and work the problems with that instead. Well, we didn't ask you to do that this semester. We're not going to do that. So you don't have to worry about that. But that is your road into, like, I don't know what this function is. First question out of your mouth is, does it have a Taylor series, and what is it? What is the radius of convergence for it? So what we're going to do is we're just going to replace our u with our 3x squared here. So this is going to be 1 plus 3x squared. I'll put it in parentheses so we can know we're substituting. Plus, we have 3x, oh, I'm sorry, negative 3x squared, because we have to do that. Plus negative 3x squared plus negative 3x squared cubed plus negative 3x squared raised to the fourth power. Okay, so we just replace that. So let's go ahead and clean this up a little bit. So this is going to be 1 minus 3x squared, square it. So we square a negative, we get a positive. We have 9x to the fourth minus 27, x to the sixth, plus, because we're taking to the fourth power here, 81, x to the 4 times 2 is going to be 8. Okay, so that would be my Taylor series. Okay, so that's kind of what I wanted you to do with that. I don't want you to recalculate one on your own. I want you to look up the one that was given to you. Now we have to figure out the radius of convergence. Now, the radius of convergence for x is the absolute value of x has to be less than 1. Okay, let's go ahead and put that in there. So we said our u is actually negative 3x squared is less than 1. So this is 3x squared less than 1. Go ahead and divide both sides by 3. We get x squared must be less than 1 over 3. X is less than, not less than or equal to, strictly less than 1 over the square root of 3. And I'm going to go ahead and do this. So this is square root of 3 over square root of 3. So x less than square root of 3 over 3. So we know that the radius of convergence must be between negative root 3 over 3 to x to root 3 over 3. That's how we figure those radiuses of convergence out. The reason why we rationalize the denominator is because back in the day when we had to use slide rules, we'll do an easy one. We'll do square 1 over the square root of 2. Okay. If you wanted a numerical approximation for this, you would need 1 into 1.41428 dot, 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 dot. So as fun as this division problem looks, actually, no, other way around. We have 1.41428 into 2. So as much as fun as this long division problem is, I don't want to do it. Okay, this would be too much fun for any one person to have by themselves. So we multiply by conjugate. We multiply by the square root of 2 over 2 to rationalize the denominator. So we have the square root of 2 over 2. So instead of this fun division problem, we have this fun long division problem. Now, we're never going to get done with this, but at least I know where to start this division problem, and I can actually start getting a numerical value for 1 over the square root of 2. That's why we used to do this. So you're still stuck with this because this was a very common thing we did in the 50s. I was not alive then, but that's how we did this in order to make sure that the people with slide rules could actually calculate numerical values for it. But that's why we're doing it. It is stuck in textbooks. It is stuck in like the thing for engineers. They do this all the time. A lot of scientists still do this. I know this is a 20th century skill and earlier. You live in the 21st century, but a lot of teachers, when you go on from this, will want you to rationalize the numerator, rationalize denominators. So it's one of those things where that's where it came from, and that's the historical reason as to why we do it. Okay, so thank you very much for watching the video. Okay, we have sound now, so that's good. And good luck studying with everything, and take care. Okay, we'll do that.